Well, good day, my ladies and gentlemen. This is going to be a very quick lightning review of the atom, quantum, and periodic trends. So let's get started right away. First of all, let's talk about the QMM. That is the quantum mechanical model. Some people might call that the Bohr model. Some people might call it the shell model of the atom. I like to call it the quantum mechanical model. Now, let's start off. There are, I think, six. I like to go with six basic ideas. Number one, there is a massive positive nucleus. Good. Number two, electrons occupy the space around the nuke. And what's interesting about those electrons is they have wave properties and they occupy specific energies, right? And we call those specific energies energy levels. That means that the electrons cannot be just anywhere. They have to be specifically placed based on energies. And when an electron jumps or switches an energy level, we say this is quantized, that it must, an electron switches an energy level for an electron to switch an energy level, the electron must gain or absorb a quantum of energy. And what does that mean? Well, what it really means is that it's just not any amount of energy, that there's a certain packet of energy, and that must have this right energy for the electron to absorb it. And when that electron absorbs it, when the electron absorbs the energy, it jumps to a higher energy level. When the electron emits, so this is absorbing energy, when the electron emits energy, it drops to a lower level, right? So the energy is emitted. And we remember that from our lab with the atomic energy spectra, right? The AES. Good. These electrons, we can only know the most probable location, right? And that's based on Heisenberg. And what do we call we can only know the probable location of an electron. That's from Heisenberg. What is the most probable called? It is called an orbital. And remember, an orbital is not a three-dimensional thing. It's not a box. It's not a roller coaster. It is just a probability distribution. Where am I likely to find the electron? We call it an orbital, right? Good. These orbital qualities are based on Schrodinger's equation. So the shapes and Schrodinger are based on Schrodinger's equation, Schrodinger's wave equation. So the shape and the orientation and how far away they are from the nucleus are all based on Schrodinger. And these orbitals, we say only 2 electrons are permitted per orbital, and that was based on Pauli, right? And each of these electrons must have a opposite spin. Okay, that is essentially the quantum mechanical model. That is the shell model, that electrons have to be in certain places. We really don't know where they are. We can only figure out the most probable location, and that most probable location is an orbital, and everything we know about the orbitals comes really from the Schrodinger wave equation. Good. And out of this, we get this whole idea of quantum numbers. Now, what are quantum numbers? Quantum numbers are just a bunch of numbers that are derived from Schrodinger's equation. But from this, we get this whole idea of the electron cloud and where electrons are. And we base it on 4 numbers. We have N, L, M, and S. N we say is the principal quantum number. It represents the energy level, right? Energy level of the electron. The L starts telling us about the shape of our orbital. I'm going to have to decrease the size of this pen. It's too fat, like I. Okay, I think we're back to here. Good. The shape of our orbital. M talks to us about the orientation, indicates the orientation, and S tells us about the spin of the electron. Energy level, shape, and orientation of the orbital and spin of the electron. That's what our quantum numbers indicate to us. Good. Now, N can tell us some other things. N is fascinating, right? N indicates the energy level. As I said, we also sometimes call this the what? The shell. So this indicates the shell. From this, I can figure out the number of electrons per shell. Well, that's going to be equal to 2n squared. So if I am at the second energy level, so let's say n equals 2, that means 8, that means I can have 8 electrons occupying that shell. The number of orbitals per shell is equal to n squared. The number of shapes of orbitals is equal to n. And so when I'm at the second energy level, once again, that means I have 2 shapes. And by the way, what are those shapes? Those shapes go in an order, right? So first I have an S, and then I have an P, and then I have a D, and then I have yoink, 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 F, G, H, and so forth. And there are numbers associated with those. When I have an S, I have a 1. When I have a P, I have a 3. When I have a D, I have 5, 7, 9, 11. So back up here to this question. When n equals 2, I'm going to have 2 orbital shapes. I'm going to have an S, 1s, and I'm going to have how many p's? 3 p's, which makes it a total of 4 orbitals, and 2 electrons per orbital means 8 electrons. Yoink, yoink. There we go, right? Good. I think that's the major thing you have to understand about quantum numbers. You no longer have to understand what the exact quantum numbers are. You don't have to give quantum numbers for electrons. That's really, I think, all you need to know. Maybe the other thing is, hey, the higher the n, the farther the electron is away. So an n at level 7 is farther away from the nucleus than farther, and if it's farther, then it has more energy, right? So an electron at n equals 7 is farther and has more energy than an electron at n equals 2. Good. Now, out of this, really out of quantum numbers, the big exciting thing that we get is all of our electron configurations are based on my quantum numbers. Good. And we have 3 major rules on electron configurations. Aufbau. Electrons enter orbitals of lowest energy first, right? That means it's going to go into a 1s before, it will go to a 1s before a 3p, right? That's why we fill the 1s first. So if you see something like this, where they show, we'll go with orbital notations, where I have a 1s and a 2s and 2 p's, and you see this kind of an arrangement, well, that is a violation of what? It's a violation of the Aufbau principle, because this electron, if it's in the ground state, really needs to be in a lower energy level, a lower energy orbital, and the 2s has less energy than the 2p. So this should be right there. Good. Next, building on this, we kind of get the, hey, sorry about that. That was a mess. Yoink. There we go. Woohoo. Good. So let's go back here to Hund's rule. Hund's is the second rule, and that says that electrons enter orbitals of same energy with same spin until each orbital of that energy has at least 1 electron, or has 1 electron. What that means is the electrons don't double up within a set of orbitals until they have to. So let's go back to our orbital notation. Notice I'm using orbital notation here instead of electron configuration notation, right? And so what that means is I would go 1, 2, 3, 4, and then I would start filling my p's this way, that I don't double up my p orbitals until I have to, because the next orbital would be a 3, right? A 3s. Now, they don't all have to be up, but they all have to be the same spin. This would not be acceptable. That's a no, right? Because those spins all need to be in the same, would have the same spin, and we represent spin by the arrows either being up or down. So that would not be acceptable. Yoink, yoink. That's the way that would go. Good. And then finally, the Pauli principle, 2 electrons per orbital, each with opposite spin. And I've illustrated that already here, right? Here we go. I've got 2 electrons in the 1s. Why do I not have 3? Because it's not allowed 3. Why are my arrows 1 up and 1 down? Because that illustrates that they are opposite spin. So showing an incorrect orbital notation could be something like this, right? I could have a 1s and do this. Well, that's wrong because I have 3 electrons in it. Or I could have a 2s and it looks like this. Well, that's wrong because both of those are the same spin. So if I have any orbital, I've got to have 1, and I can have no more than 2, and they have to be opposite spin. So that would be the correct way, whether it's a 1s, a 2s, or a 2p. Good. Now, speaking of electron configurations, let us talk real quickly about how we do that. I use the periodic table, and remember, here's the way we think about it. Here I have an S block. Here is my P block. Here is my D block, and we won't worry about the F block. And I would have what? This is an S1, and this is S2, and this is P1, P2, P3, and so forth, right? And here are my Ds, D1, right? The easy way to remember is the orbitals take, orbital notation takes a form of N, X to the Y, where N is the energy level, or my shell, X is my subshell, and Y is number of electrons in subshell. So these subshells are going to be my S, D, P, and so forth. And N will tell me the level. And what we have to remember is for my P's and S's, N equals my period number. And for my D's, my N is equal to period number minus 1, meaning my D is always 1 less than my, let me put it this way, my D is always 1 less than the number in front of my S's. So if my S is a 2, that means my D is a 1. Well, that won't happen because there's no such thing as a D1. Okay, so that's just a reminder. So if we're doing something like this, here's vanadium. It is a 1, 2, 3. It ends in a 3, a D3, right? Now, where do we start? We start always up here. So we go 1s, 2, 2s, 2, 2p, 6, 3s, 3s2, come over here, 3p6, and then 4s2. Here's my 4s2, and now I'm to my d's, right? And my d's always have 1 less than my s's, so I'm a 4s, so that means this is a 3d, and what did I say? 1, 2, 3. That's how we do electron configurations. Okay? Got it? Cool. All right. Let us move on. Let's go back. I hope that's a good enough refresher for you on electron configurations. Here we go. Paramagnetism. What is paramagnetism? That means that the element is attracted to a magnetic field. And why is this a discussion that we're having now? Because that attraction is based upon unshared electrons. So if you take something like nitrogen, 1s2, 2s2, 2p3, there we go. It has 3 unpaired electrons, so it will be attracted to a magnetic field. It's based on the spin of these unpaired electrons that is attracting it to a magnetic field. So we'd say that nitrogen is paramagnetic, right? Now, what else is paramagnetic? Something like oxygen. Oxygen would be paramagnetic, right? Because it's 1s2, 2s2, 2p4. I hope I have oxygen right. 1, 2, 3, 4, 2p4. And so that would mean what? For if we just look at this, it's better to look at the orbital notation when we're thinking about paramagnetic, right? Here I have a paired electrons, and then I have 2 unpaired electrons. Because of these being unpaired, it would be paramagnetic. Yeeks. Okay, good. And finally, valence electrons. These are technically these are electrons involved in reactions. However, by the way we kind of identify them is we say that they are electrons in the highest right? They're in the highest energy level. Good. And the easiest way to know that is look at our periodic table once again, because the periodic table tells us almost everything here. Whoops, what a mess. Let's clean up some of this. Go. Woohoo! Let's get rid of this. Oops. Good. Periodic table. 1 valence electrons, 2 valence electrons, 3, 4, 5, 6, 7, 8 valence electrons. And in this area, most are going to be 2. And why is that? Well, let's take a look back at our vanadium. We said it was 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. Well, I said that my valence electrons are in the highest energy level. What's the highest energy level? The 4 there. So what are my valence electrons? The 4 s's are my valence electrons. Good. Now, by the way, when vanadium becomes an ion, which electrons is it going to lose first? It's going to lose the electrons in the highest energy level first. So a vanadium 2 plus is going to lose these electrons, meaning it will have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d3. That is the electron configuration of vanadium, right? Okay, good. Let's move on. I hope that's good enough for valence electrons. And let's talk about another very important thing, and that is periodic trends. Now, periodic trends are really all based now, I think, on Coulomb's law. Think about Coulomb's law when you're thinking about periodic trends. Now, what is Coulomb's law? It says that the force of attraction between a positive and a negative, or a positive, positive, negative, negative, is equal to K Q1, Q2 over R squared. Now, how does that relate to an atom? Well, with an atom, it's really a force of attraction between the nuke and the electron. Now, this K stays the same. We don't care about it. It's just a constant. Now, Q1, we can think of that as the charge of your electron. And Q2, we can let that be the charge of your nucleus. And for us, we're going to call that the Z effective, the effective nuclear charge over R squared. And what is R? R is going to be the distance between electron and nuke. And what that is really a surrogate for that is atomic size. Because the bigger my atom is, the farther my electron is from my nucleus. So if I have a big atom, a big size, that means R is going to be bigger. For a small atom, that means R is smaller. Now notice R is in the denominator, and it's squared. So when I'm looking at my force, how do I get a big force? Well, a big force is going to be related to, now my charge of electrons stays the same. So a big Z effective, since it's in the numerator. And what do I want for size? I want a small atomic size. That's how I get a big force. Good. All right, so we're going to explain all these periodic trends in terms of that. Z effective, what is Z effective? This is the effective nuke charge. And let me get rid of some of this. That is essentially the number of protons minus shielding electrons. And what are shielding electrons? Well, those are what we would call our core electrons. And what do we mean by shielding? Okay, so I have something like lithium here, and I have 3 protons, and then I have a couple of electrons in the 1s, and then I have another electron in the 2s. Now, this electron is going to be attracted by those 3 protons. However, since a negative and a negative repels each other, these 2 electrons in the core, in the 1s, are pushing away. So this electron does not feel 3 protons, it feels something less than that. And a rule of thumb is take your number of protons, in this case 3, and subtract your core electrons 2, and that will give you a rough idea of the effective nuclear charge. So this is core electrons, and this is number of protons. And how do I figure out my core electrons? Well, my core electrons are the electrons that are not in the energy level, the same energy level as your outer. So if we looked at, let's say, nitrogen again, 1s2, 2s2, 2p3, my electrons, my outer electrons are in the second energy level, so my core electrons are going to be my 1s. Or another way to know your core is when you write the noble gas method. Helium, 2s2, 2p3. Here is my core. These are my core electrons. Good. So that's the definition of Z effective. What is the actual trend in Z effective in my periodic table? So let's go to a new clean periodic table, which won't be clean for long. Z effective, very simply, as I go from left to right here, what's happening? I am staying in the same shell. My electrons are in the same shell. These are all in the what? These are all in the 2 energy level. So the shell, it's in the second shell, but I am adding protons. So as I go from left to right, my Z effective increases. All right. As I go down, my Z effective still increases, but not as much. I have I'm adding protons, and so my Z effective does increase, but you're going to see it doesn't have the same effect, because as I go down, what am I also doing? I am adding shells, right? I go from the second to the third to the fourth to the fifth to the sixth to the seventh shell, meaning my size is getting bigger. Okay, good. So that's our trend on Z effective. Next, let's go back and take a look at atomic size. Atomic size is really going back to this. The stronger the force, the smaller the size. The stronger the force, the smaller the size. Got it? Good. So I think we can go directly to our trends. So I need to grow another foot so I can do this easy, right? Let's take this down. Good. Get rid of that. Let's put our ubiquitous Q1, and I'm going to put Z effective here, and I'm going to put R squared. We want to explain all these things in terms of Coulomb's law. So what's going to happen as I go from left to right in a period, we said that my Z effective is increasing. So Z effective is increasing. So that means I'm having a stronger pull on my electron cloud. If I have a stronger pull, that means this is going up. That means my force of attraction goes up, and that means my size is going to do what? Since the nucleus is pulling stronger on the electron cloud, my atomic size decreases as I go from left to right. Now, as I go down a group, what am I doing? In each of these cases, although my Z effective is going up, I am adding a shell, as I said, and so that means I am, so here's an electron and another shell and another shell and another shell roughly, right? These are not real lines, but that gives us an idea, right? So as I go down, my size is increasing. So my atomic size increases as I go down. And why is that? Because I am adding electron shells. Got it? And once again, why did my size go down as I went from left to right? Because my Z effective went up. Okay, good. Next. Aha, ionization energy. Okay, so ionization energy, what is ionization energy? It is the energy required to remove an electron from an atom in its gaseous state. There we go. And since I am removing an electron, right, I am pulling a positive away from a negative. This is always endothermic. This is always a delta H that is greater than 0. So that's the first ionization energy. The second ionization energy is where you're taking an electron from the ion. Once again, it's gaseous state. Sorry, folks, gaseous state. Mg2 plus gaseous plus 1 electron, right? Now that is also endothermic. Which is bigger, the first or the second? Well, in both cases, we have the same number of protons, but I have fewer electrons in the second case. So that means my ionization energy, that means I'm going to take more energy. My second ionization energy is always greater than my first ionization energy, right? And when do we see the biggest ionization jump? The biggest jump is when I'm pulling an electron out of the core. So what's, magnesium? Let's write magnesium real quick here. So magnesium is 1s2, 2s2, 2p6, 3s2. 3s2. I should have written, I'm going to write this in electron configuration here. Well, yes. So I'm going to write the 3s. So it's 1s2, 2s2, 2p6, 3s2. Good. So yoink, 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 yoink. Na, 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 na. There we go. So that's magnesium. 3s2. Good. So magnesium plus 1 is that. Now when I take, so that's magnesium plus 1. When I remove, so that's the first ionization energy. Now I remove this one, and that is the second ionization energy. Now notice, what do I have left? I have a core, right? This is my helium core, and this would be my neon core when I look at all of this. So that's my neon core, right? To remove an electron now from this is going to take much, much more energy than either of these. So for magnesium, it's going to be much, much harder to take that third. And so when you're looking at a table, if you have something like, 10,000 and then 5,000 and 3,000 for your ionization energies, and this is 1, 2, and 3, you see this big giant jump. That means that you are removing this electron from a core. All right? Good. Now let's take a look at trends real quickly. Trends. Nah, 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 nah. Here we go. So let's use the magic finger and clean this up. Yoink. Yeah. So what are my trends in ionization energy? As I go from left to right in a period, what happens? Size does what? Size goes down. Z effective goes up. So my Z effective goes up. My size goes down. What happens to my force? My force goes up. So that means my ionization energy increases. Good. As I go down, what happens? My Z effective goes up, but my size goes up a lot. All right? So if we look at this effect here, indeed my Z effective goes up a little bit, but my R goes up a lot, which means overall, since this R is a squared term, my force decreases. So that means my ionization energy goes down as I go down a group. Got it? Okay, now there are a couple exceptions, and we need to talk about those exceptions. First, we have the exception of magnesium and beryllium. These two are an exception compared to these two. And we said the trend is that as we go from left to right, it gets harder. However, it is easier to remove an electron from boron than it is. So it's less ionization energy for boron is actually less than the ionization energy for beryllium. That goes counter to the trend. Now, why is that? Well, in beryllium, I have a we'll just look at the second energy level. I have a 2s2, right? That's beryllium. In boron, I have a 2s2 and 1 2p. So you're removing a p in boron from, and you have to remove a shared s2, a 2s in beryllium. And it's easier to remove this 2p from boron than it is to remove this 2s from beryllium. So that's the reason. Some people will say that the S penetrates closer to the nucleus than the P, and that's why it's easy to remove. Others would say that in this case, the 2P is actually farther away, that the R gets bigger, and so the force is less. In any case, the reality is it's less difficult to remove this 2P from boron, which goes against the trend, right? Because we said as we go from left to right, ionization energy increases, but not with boron. And that holds true also with aluminum. Now, the next exception to the trend is right here between my nitrogen, oxygen, and phosphorus and sulfur. When we look at nitrogen, it is 2s, 2p, right? 1, 2, 1, 1, 1. And when I look at oxygen, it is 2s, 1, 1, 1, 2p, yoink, 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 yoink. And here's what the truth is. The ionization energy of oxygen is less than the ionization energy of nitrogen, which goes against the trend. We'd expect, since oxygen is farther to the right, to have a higher ionization energy. Why is that? Because in oxygen, the electron that is being removed is coupled with another 2p. So there is going to be a repulsive effect here from the coupled or the paired electron. Got it? So it is easier to remove this electron from oxygen because it is paired with another in the 2p orbital, whereas all the electrons in the nitrogen are singlets. All right, and that same thing holds true with phosphorus and sulfur. Good. We are almost done. I want this to be quick, so let's finish it off. I think we've covered our exceptions. And what else do we need to do? Electron affinity. Electron affinity is kind of the opposite of ionization energy. Ionization energy is the energy required to remove an electron. Electron affinity is the energy gained or lost when an atom gains an electron. And so we're looking at something like chlorine, gaseous state, and we're going to gain an electron, and it's going to form chloride in the gaseous state. That is my electron affinity. Now, electron affinities can be endothermic, or they can be exothermic. Excuse me, I did that wrong, didn't I? No, I did that right. Exothermic. And the ones that are exothermic are for the things that tend to form anions more readily. And those happen to be what? My halogens in general. So let's take a look at the general trend on electron affinities. by and large, here's all I want you to know. As you go left to right here, my electron affinities become more negative. Okay, meaning more energy is given off. Excuse me, we don't talk about the noble gases here, right here. My halogens have the most negative electroaffinities, and that means what? Most energy released when they gain an electron. That's really about all I want you to know. There are exceptions similar to the ionization energies, but just know that halogens give off the most energy when they are gaining an electron. Okay, I think that is it. I hope I have not gone too quickly, but that should do it. Okay, see you next time.